Okay, let me introduce the next presentation. Shall I wait a minute? Wait 1 minute or 1 or 2 minutes? And now the time is 33 minutes and now just 34 minutes. Okay. Okay, let me introduce the next presentation. The next presentation, next paper is entitled, Backpropagation. Backpropagation-based background compensation of TI-DAC errors in high-speed transmitters. This paper is presented by Dr. Agustín Galetto from Fundación FULGOR, Argentina. So, are you ready?
Yeah, I'm ready. Can you hear me?
Yes, loud and clear.
Okay, thank you.
Yes, please start.
Thank you for your kind presentation. My name is Agustín Galetto, and I'm from Córdoba, Argentina. And I'm an electronic engineer, and I'm currently pursuing my PhD in microelectronics. I'm a member of the Microelectronic and Analog Design Group of FULGOR Foundation, and today I'm going to present our work entitled Backpropagation-based background compensation of time-interleaving digital to analog converter errors in high-speed transmitters. So first, I'm going to talk about the motivation of this work, and after that, I'll give a brief introduction about the operation and impairments of time-interleaving DACs. Then I'll summarize the state of the art in compensation and calibration of TI-DAC errors. Next, I'm going to present our proposal, followed by the simulation results, and finally some conclusions will be drawn. So here we discuss high-speed time-interleaving DACs in the context of digital communications. So next generation transceivers will operate at high baud rates, which will require sampling rates and bandwidths higher than 200 giga samples per second and 64 gigahertz respectively. And today, time-interleaving is the most employed technique at the industry. And to reach high-speed operation, high parallelism is required, which will become very challenging due to the mismatches. Moreover, mismatches become more significant in new technologies. So while increasing modulation scheme, better performance is required, so better calibration and compensation techniques are needed to overcome the errors. Here we can see an example of 2 times interleaved DAC with ideal zero-order hold return to zero response in sub-DACs. And at the right side of the slide, we can see the ideal output. Here, an amplitude mismatch is introduced between sub-DACs, affecting the output, as you can see here. This kind of errors and others produced by impairments like bandwidth offset, bandwidth mismatch, and timing error. Here in literature, there are many approaches that intend to correct the before mentioned problems. Here we can see a diagram of foreground calibration, which needs ad hoc circuits and known signals to implement the calibration. This implies the interruption of communication, which is undesirable. Now, here we have a background calibration system, which doesn't need to interrupt the communication, but cannot correct every impairment at the same time. With the same circuit, which supposes the elaboration of many dedicated circuits to counteract each one of the aforementioned impairments. Here, there is a more general implementation where the same equalizer can counteract all impairments, but here the need of known signals means the interruption of the communication. So finally, we can see here the most promising architecture which operates in background and can counteract all the impairments concurrently. To sum up the discussion, in this table we can see examples of the aforementioned systems. First, calibrations, which cannot correct all impairments. Then foreground compensations, which interrupts the communication. And finally, our proposal, which intends to compensate for all the errors while the system is still in transmission. Now let's get into the details about the operation of our proposal. Here we can see a simplified diagram of an error backpropagation based compensation system. Error backpropagation technique is extensively used in neural network training, and we propose to use it to estimate and compensate analog mismatches in time interleaving DACs, achieving background operation, low complexity, and concurrent compensation. So first, the system needs to estimate the behavior of the full DAC, including the errors among the interleavings. This is achieved by the channel estimator here. After that, the error backpropagation block, then the system needs to calculate the error between actual output and the transmitter and the desired signal, which is a pulse-shaped digital communication signal. After that, the error backpropagation block processes the error and make it useful to adapt the coefficients of the impairment equalizer. A few slides before, we said that the proposed system can achieve background operation, low complexity, and concurrent compensation. So let's see why is that possible. First, as regards the background operation, the key is that the signal used to calculate the error used to adapt the coefficients is a digital communication signal. That way, communication doesn't need to be interrupted. As regards to the low complexity, it's possible to implement all the estimation and the compensation engine in firmware. Another interesting feature is that is the possibility to operate the feedback with decimation. And it's important to note that the complexity of the impairment equalizer is similar to the complexity of a pre-emphasis filter commonly used in regular transmitters. To finish the low complexity discussion, it only left to say that the adaptation engine can be stroked and still be able to track and compensate the errors. Finally, as regards concurrent compensation, it's important to note that the proposed compensation system does not need to assume any one of the impairments to be compensated before starting to compensate another. This is that it can correct every impairment at the same time. Now, let's take a look into the setup for the simulations used to evaluate the system. Here you can see a simplified diagram of the whole compensated transmitter. For the simulations, we used 128 gigabytes communication with 256 QAM modulation and with a non-dispersive channel. The TI-DACs used here are 2, 4, and 8 times interleaving. It means that TI-DACs contain 2, 4, or 8 sub-DACs with impairments, with bandwidths of approximately 64 gigahertz plus 10% of extra bandwidth and 8-bit of resolution. The impairments applied to the system are gain 9% of the nominal amplitude, offset 5% of full scale voltage, and time skew or time sampling error of 3% of the period of the baud, and bandwidth of 3% of the nominal bandwidth. As regards the feedback, we assume full bandwidth, but a decimated or subsampled feedback. And finally, we used ideal receptor to evaluate the signal. So here we can see the degradation caused by a randomly distributed set of impairments in 256 QAM constellation at the left side of the screen. And at the opposing side, there is a constellation of the resulting output of the same transmitter with the same sets of impairments after the compensation converges. Note that the number of sub-DACs in each time interleaving DAC is 8. Here we can see the histograms of VERB for a time interleaving DAC based transmitter of 2, 4, and 8 sub-DACs, 2, 4, and 8 sub-DACs in each full time interleaving DAC. Over 800 cases were simulated for each configuration, and for each case, the compensation was turned off and turned on to collect uncompensated and compensated results. Impairments were introduced as uniformly random distributed variables, and the magnitude of error for each impairment can be seen here at the bottom of the slide. The target bit error rate for the compensated case is 6 times 10 to the minus 4. And as you can see here, the compensation systems can reach really close to the target. So this is a really great result. To analyze the analog behavior of the TI-DAC with and without compensation in terms of signal to noise and distortion ratio and spurious-free dynamic range, we implement the setup you can see here. It's important to mention that it's not a normal mode of operation. Here we use it only for evaluation purposes. The background compensation system is freezed, and we use the coefficients with the compensation. We took the communication signal off and put and replace it by a sinusoidal tone. We freeze the compensation system, and we evaluate the output for the cases with and without compensation. And here we can see the degradation caused by the spurious here, provoked by the impairments in a 8 times interleaving TI-DAC without compensation. And the right side of the slide here, we can see the elimination of the spurious due to the great compensation of the system. Well, to finish the presentation, let's take a look on the final conclusions. We can assure that digital equalization combined with backpropagation enables background estimation and compensation of impairments in TI-DAC-based digital communication transmitters. And all the analog impairments, estimation and compensation are done concurrently without interrupting the communication. And the estimation and the adaptation of the coefficients can be achieved by firmware. And impairment equalizer complexity is similar to the complexity of the pre-emphasis filter used in regular transmitters. And decimation and strobing can be used slowing the convergence, but lowering the complexity and the energy consumed of the system. So thank you for your time.
Thank you. Do you have any comments or questions, comments, please?
So yes, I have a question. Patrick Arts here.
Okay, go ahead, please.
Yes, thank you for the presentation. I have just a short question about the ADC in the feedback loop. So I understood that it requires the same input bandwidth as the output bandwidth of the DAC, right?
Yeah, you're right. Here in this work, we assume that the bandwidth of this component is the same as the output of the transmitter, but that can be achieved, for example, using only a single SAR interleaving of the set used in the receptor. So we reach full bandwidth, but decimated sampling rate.
But don't you get the same time interleaving problems then, with that you also have to correct everything? So aren't you shifting a bit the problems to the ADC now?
No, this wouldn't be the case because we use only one sub ADC. For example, in the receptor, to support the full rate and the full bandwidth, we should use, for example, 128 SAR in a time interleaving SAR ADC. Yeah. Here we can use only one of the 128. So we shouldn't have interleaving here. We just use one SAR with the full bandwidth, but decimated sampling rate.
Okay, but you still need the whole analog front end, right, to achieve the full bandwidth for the ADC?
Yeah, the track and hold should support the full bandwidth. You're right.
Okay, thanks.
Thank you.
Thank you. Any other questions? No. Could you show again the slide of the constellation? Is that the simulation result?
Yeah.
This one, yes. And this is 256 QAM and could you show again the other conditions, for example, the symbol rate or
Yes.
Okay, 128 gigabytes. This is let me confirm. This is a single carrier modulation, right?
Yeah.
Not multi-carrier, but single carrier, right?
Yeah, single carrier.
So okay, I see. Thank you. Any other questions? No. So are you intending to apply this this type of DAC for example, the millimeter wave communications, millimeter wave radio?
Yeah, here we are developed the system and intend to apply in every kind of communication. It can be used in wireline, wireless, or optical communications. Actually, the problem with the feedback, which is not a problem, but we are trying to improve this, making it possible to use a reduced bandwidth feedback, but that's a work in progress, and that could improve really much the system.
Okay, I see. Thank you very much. Any other questions? We have a couple of minutes more. No? Okay, thank you very much for your presentation. Yeah, yes.
No, I wonder if the 3% of time error and the 3% of bandwidth error are the limits, or that is only the example here?
No, it's not the limit. It's just what we use to simulate these results and the random Monte Carlo simulations. But there are the possibility to extend this. It's a really robust system, so this can counteract more harmful impairments.
Okay, thank you.
Thank you.
Any other? Another question acceptable? No. Okay, thank you very much for your presentation.
Thank you for your time.
So